Okay, great. Thanks everyone for coming. I'm really stoked to be here today speaking to you at Cloud Next. My name is Chris Broadfoot. I'm an engineer on the developer relations team. And today I'm going to be talking to you about minimizing app latency at scale. And I'll go into a little bit about what I think that means. I spoke to some people outside as we were waiting to come in, what it means to them and what they are trying to get out of this talk. And there's little bits for everyone, I hope. But we'll generally be speaking at a pretty high level. I'm going to give you some ideas and draw on some of my personal experiences working on production apps at Google. Even though I'm in developer relations, I've had some side projects, essentially 20%. And I'll show you some real graphs and screenshots too. So notes and slides will eventually be at this URL. I'll be referencing some things, and you'll be able to find links under that link. So yeah, performance and latency is a really difficult subject to talk about at this conference. You might have noticed that it's one of this talk is one of the few that are sort of talking about things at a high level. We're not talking about specific products or anything like that. So you're probably a really diverse audience of mobile, web, backend developers. There's probably some of you in IT and ops as well. So I'll be trying to keep things sort of general and give a bit of information for everyone. I'm going to take a holistic approach, which I think is generally the right way to approach performance and latency and things like that. So why are you here? Why do we care about it? You've probably already acknowledged that you care about latency because you're here or watching this talk on YouTube. This is a pretty famous quote, and it's kind of become a rule of thumb, I think. So Greg Linden, who at the time was at Amazon, this was about 10 years ago, I think now, found that 100 millisecond increase in page latency caused about a 1% drop in revenue. And we're 10 years on now, but I think these results are still kind of correct, and they've been replicated across multiple companies, including Google and Bing. And I'll have some links to some references for this. But yeah, does this really apply to you? That's the question. Does this apply to your app? Obviously, if your app doesn't have revenue, then it doesn't at all, right? OK, let's first define latency. It's essentially the delay between request and response. But what's application latency? You came here to this talk. The title is Minimizing App Latency. OK, I think it's just a made-up term. There are about 30,000 results on Google. So I'm going to define it here today. So application latency, I'm proposing, is the delay between a user's action and update. So this is essentially a holistic UX thing. So the latency is the time the user presses a button or initiates an action and when they see a result. So this is actually nothing to do with networking or anything like that, although it is related. When does it matter? A good rule of thumb is that your most common cases should be faster. So given a blog service, viewing a blog post is the most frequent action, maybe. A lot of blogs are not read very often. Going down to viewing the comments for a blog, so maybe as you scroll down, load those in later. Commenting on a blog post and publishing and editing, so essentially the right operations. And then finally, the most infrequent operation is creating a new blog, although perhaps more blogs are created than posts are created. So that might be the wrong thing to optimize for. There's an interesting anecdote, which I think was from Blogger. The blog creation process, that is creating an entire new site, was so fast that users thought that something was wrong. They would click create new blog, and boom, it would just happen. And I think that left users wondering whether something really happened at all or not. So sometimes fast is not better. Optimize for user satisfaction over everything else. So we might be able to change from frequent to infrequent to insignificant to significant, right? Maybe significant operations are slower because the user is committing something, so maybe they expect you to commit something back, right? So they expect something to be slower. So the next thing I want to talk about is managing user expectations, right? When can you get away with making things slow? If you can't make things fast, then make the user understand why things are slow, right? I think we can all understand that re-architecting our applications in a way to make things fast is sometimes not possible. So when can we get away with slow things? We already talked about more infrequent operations. Just telling the user it's going to take a while might be good enough. and more importantly, telling them why it's going to take a while. Giving users frequent updates and indications is also really good. Tell them why it's happening and what's happening under the hood. So an app that does this really well is just the BigQuery user interface. There could be some improvements, obviously. But what it does, when you hit run query, it just has a timer, a stopwatch that goes up. And so this is giving users some indication that something is happening. They don't really know exactly what's happening under the hood. Although once the job is completed, you can see the explanation for the query. And it tells you, importantly, how many gigabytes were processed. So it's telling you why this operation took so long, right? Because we processed all of these gigabytes of data. So this sets user expectations. They know they're querying huge data sets, but they're only happening in 17 seconds. Whereas this operation, obviously, something taking 17 seconds might not be appropriate for other applications. I'm thinking about like game servers or something like that, where we're talking like tens of milliseconds rather than tens of seconds, right? So you have to consider everything in context. So breaking down at a really high level, application latency. We can think of things, so on the left of this slide would be the user initiating an action, and on the right, when they see the actual update. We have any network requests, which I think a lot of people here are concerned about, which consists of latency of the request going out, whatever's happening on the server, and maybe dependent servers from there, and then the time it takes to come back. And there may be some sort of on-device processing, like storing the results in a local cache or database, and then whatever happens in the UI. So like reflows and repaints. These are all part of application latency. So this is what the user experiences. So one trick that you might know is to sort of decouple these things to reduce the perceived latency. So maybe doing some of this work up front, and sending off the network request in the background. A really good example of this is anything with a like button or a +1 button or something like that, right? The UI updates instantaneously. The app confirms that the user performed an action, and the network request happens in the background. So you might do some sort of on-device processing beforehand, like storing the fact that the user initiated this action, so that you could possibly retry the action in future, or display that the network request failed, or something like that. And I'll actually be using this graphic. We're going to look at each of these boxes separately throughout the talk. So we're actually going to start more from the UI side. We've been talking a lot about UX stuff, but yes, we will be talking about networking and things like that. OK, so how do you know what the slow part of your app is? We need to figure out what's slow and how to fix it, and what the problems are. Google Analytics does this automatically for web applications. This is actually a real app that I've worked on. I've anonymized the page URLs, but it gives you a really nice indication of several important statistics. In this case, the document interactive time, which is when the page can be interacted with. So this is separate from DOM content loaded if you're a web developer, which I think is a poor metric. This is a better metric. So this is a really simple way to figure out which of your pages are slow. So once you've figured out which pages are slow, using the Chrome Developer Console or the equivalent for Android or iOS, it's a really good way to figure out exactly what's happening. So this is actually a timeline graph of Gmail, which is an incredibly complicated application. So it shows you things like what JavaScript is running, what network requests are happening, and what paints and things like that are happening, like compositors on the GPU, things like that. So you can figure out exactly what's happening inside your application. Detecting the document interactive time and DOM content loaded are good, but even better is getting actual timings from your users. So you might have some sort of lazy loading or something like that. With Google Analytics, you can send these timings to Google Analytics, and you'll be able to slice and dice it like any other events or triggers or anything that happens inside Analytics. So this is a really handy way to customize your timings once you've figured out exactly what components of your page or application that you want to figure out. So this is the same code for Java, so on Android. And you'll end up in the analytics with a graph like this. So this is a real app, again. So you get timing buckets. The most interesting thing, I think, for me, are the ones that take the slowest. I want to figure out how many of my users are going to become disengaged. So anything above, I think, a good rule of thumb, again, is about 3 seconds. After 3 seconds, a user is going to become disengaged. And we can figure out globally where these users are. So I'm from Australia. Things are really slow in Australia, generally. And it's no different for this particular application. Although I think these statistics are faulty. 840 seconds is a long time. I don't think things are that quite bad. But yeah. So yeah, going back, let's talk about network requests now. Why are things so slow from Australia? OK, so a good first step, if you haven't already, is setting up monitoring for your backend or your front end. Both are good. This is just the way to add an uptime check in StackDriver monitoring. And after you do that, it'll send a request every minute or however often you want, and give you a graph like this. So it's important to note that these are actual timings from StackDriver, not an average of all of your user requests or anything like that. So this is really good for detecting if your app is up and getting a sense of how long things are taking on your backend. But it's only measuring things from the perspective of the StackDriver probers, right? These are not actual timings from your users. So it's really not that useful. It's good for keeping track of uptime, but not for identifying issues. So how do we identify issues? Using tracing. And those user metrics are really important too. So now we're sort of diving into this remote processing, like whatever's happening on your server. Why are things happening so slow? Why are the requests taking so long? So StackDriver Trace is the way to do this. This is enabled by default for App Engine Standard. And this app is actually an App Engine Standard app. And you get this nice dot plot graph showing requests over time and whichever ones were sampled and sort of where they are. So on the y-axis is the latency. And you can see some of the requests are getting up there over that sort of 3-second mark where we're getting concerned. And generally, the slower ones are the most interesting ones to look at. And you can actually click on these specific dots to look at the traces of those specific requests. And there's also this sweet auto reload thing, and you can see the traces come through live. Another really interesting view in StackDriver Trace is this latency profile. So the graph in orange is this week, and the blue is the previous week. It's actually really interesting that this app has such a consistent latency profile. I'd expect these things to change, a fair bit week to week. But yeah, this is a really great way to see how many of your users are in sort of each bucket that you care about. So there are some users above that 3-second mark. And you'll be able to see sort of like the percentage of people that are becoming disengaged. The comparison is also interesting to detect regressions in your application performance. So StackDriver also produces reports. It'll provide sample traces for each sort of percentile buckets. So again, I think the most important ones to look at are the slowest ones. So this is a single trace. This is one of the slower ones inside this particular app. Running on App Engine Standard, you can see it's doing a bunch of memcache, data store requests, and then sort of nothing happens after the 1-second mark, right? We have no idea what the application is doing. So what happened there? I don't know. I haven't instrumented this particular app, but using the StackDriver API to provide custom spans. So each of these particular timings is called a span. It's the way to do that. There's also a Zipkin integration. So if you're already using Zipkin for traces, well, if you're using who here is tracing already? Oh, OK, that's a pretty good amount. So if you're using a tracing product already, there might be an integration with StackDriver. With Zipkin, you can send all of those traces to look at them in this great UI. But yeah, so how do we mitigate these slow requests? So for example, here, maybe there's some sort of processing event or something like that happening. We don't know. So how do you mitigate them? I think a really good way to, and if you can afford to, is to write these requests to low latency event queues and other services. So I'm not going to teach you how to create an event pipeline or anything like that. But what I'm essentially suggesting here is to store these payloads somewhere else temporarily before you can process and ingest them. So make those client requests asynchronous. I've talked to a bunch of people outside who are using App Engine. Task queues are a really good way of doing this. Very high performance. You can put those requests in there and process them with a push or pull queue as you have capacity to do so. The rate that you do that might rely on whatever underlying services you're using. So if you're using data store, for example, you might only want to write 100 requests per second or something like that. Cloud storage, Spanner, and PubSub are also really good. Spanner and GCS cloud storage have multi-region modes, which means that if your servers are globally distributed, you'll be able to write into those quickly. And REST support for task queues is coming soon, so you'll be able to use those outside of App Engine. So maybe we identified a function or a handler that's performing poorly. I think the next thing to do is to profile that function. So pprof is an open source tool from Google for visualizing and analyzing that profiling data. You get the profiling data through other tools like Linux's perf tool. And this is generally good for things that are CPU bound or IO bound or something like that. You can figure out exactly what's happening. So on the left is the output from the pprof command line tool. Basically see the top functions. You can dig in deeper through different methods. And on the right is a very complicated graphical output, which shows you basically like call graphs and how long things are taking. I think the larger boxes are things that take longer, or where more CPU time is spent. And another really great way to visualize this is using a flame graph. So the colors actually don't mean anything. I think that's where the name flame comes from, though. Basically, the width and the x-axis isn't anything to do with time or anything like that. The wider the block, the more often it shows up in stack traces for the profile. And at the very top are the things actually spending CPU time. So this is a good way to identify potential things to fix. So in this one, I don't know, like optimizing text template or something like that. Maybe adding a caching layer there is appropriate. So after you've figured out a particular function or method that needs to be improved, benchmarking is a really good way of doing this. I always say to profile first, otherwise you're kind of benchmarking in the dark. You really want to figure out what to benchmark first and find problem areas. It's also really important to replicate these results in production. So production environments differ greatly from your workstation in terms of their performance characteristics. So there's things like hypervisors. There was an interesting story, I think, a couple days ago about the get time of day syscall taking a really long time on. It wasn't GCE, but another cloud provider. So you might have problems like that only manifest themselves in production. So you really need to run these profiling and benchmarking on your production environment. Generally, these VMs have a lot of raw processing power. Obviously, it depends how big your VM is. And there might be different characteristics for writing to disk or anything like that, right? Like if you have SSDs or a network-attached disk or something like that, your application might perform quite differently. Another way your application performance might change is under load. So it's really, really important to do load testing. I worked on an application a few years ago that completely fell apart under load. Right? It ran really quickly when a small amount of load was sent at it, but once it was replicated and out in production, many different clones of the service, it just didn't scale once actual load was sent at it. So this is a good thing to do. Okay, let's talk about getting close to your users. we're going to talk about network latency now, basically. So the request and response latency. OK, so back to StackDriver monitoring. This is another interesting plot. The one I showed you previously aggregated all of the latency profiles from all of StackDriver's locations, but this one splits them out separately. So you can see here the orange line, which is generally at the top, or the pink one, which is Sao Paulo and Singapore, respectively, are the slowest ones. Presumably that's because this application is hosted in the US or something like that. So this is a really good way to get an idea of how your application performs across the globe from your different users. So you might not actually care about this. I was talking to someone who has an application only for US users. This is not going to be useful for them, right? But if your Google Analytics tells you that you have users across the world, the poor sods in Singapore or Australia or whatever, the app is really slow for them, and maybe you had no idea, but this is giving you an indication. And if we zoom out this graph, this is another production app, by the way. I won't say which, but if you zoom out, you also see these huge spikes across the week, right? I have no idea what happened there. But this is another great way to figure out when to dig in a little more, right? It's interesting that this application spiked only in certain regions, right? Why is Singapore so slow for over a day? There's also a lot of variance from the other regions there too. So maybe there was an outage or something like that. OK, so now you figured out where your app is slow. The thing to do is to figure out where your users are, put things close to them, whether it be front-end servers, so you can serve out your content to them, or backends, so maybe like replicating, distributing data that's important for them. So for example, if you have users in Asia, maybe you probably want to store their data closest to them so that they can access it really quickly. Maybe you also replicate it across to other regions, but it should be available close to them. So this might be something like a read-only replica. And you'll have a trade-off here between lowering latency and data consistency across the world, right? A write that happens in Asia it's only possible to make it to the US 200 milliseconds later, right? So if a user in the US is trying to read from it, they'll see something different. You can't beat physics, right? So there's trade-offs to do there. One really easy way that will be available soon to mitigate this is using Spanner, which will have a multi-region database. So that was actually demoed this morning, the multi-region database. So that'll hopefully make things quick to access from any region. OK, so once you have all these servers across the world, you need to use load balancing. And the cloud load balancer gives you intelligent routing based on the location of the user. And so if the closest instances don't have enough capacity, then it will send the request to the nearest region after that. So you'll always be hitting the closest servers to your user. It also gives you things like automatic logging, including latency statistics. So from the perspective of the load balancer, how long did things take? So this is really good, and it's a pretty easy thing to enable. And it also integrates really well into Cloud CDN, which is not really like a traditional CDN where you give them all of your assets and they distribute them across the world. But it uses Google's globally distributed edge points and points of presence, and they cache HTTP traffic and requests closest to your users. So caching things at the edge of Google's network provides faster delivery of content while reducing serving costs. So these requests aren't being sent across networks. It's closest to your users, fast and cheap. So these are the points of presence. I think the blue dots, the dark blue dots, and the blue lines represent Google's network. And there are many peering partners as well. So it was mentioned in the keynote this morning, actually. So the peering partners mean that it's likely there's only one hop between your users and the content that you need to serve to them. And this also means that as much traffic as possible is sent through Google's network. So even if that request does need to go from Asia to America, it's happening over Google's network. You've heard all about the excellence and performance of the network this morning. But yeah, this is a really great way to go. So it's really easy to enable. On your load balancer config, you just hit a checkbox. I don't know why you wouldn't do it. Maybe if you're concerned about content being stored in different places, but just hit enable or run this gcloud command, and it will just work. And by just work, I mean you need to do a little bit of work. Not all HTTP responses are cacheable. It'll only cache ones that meet these criteria. So in short, there's a bunch more inside the documentation, but basically it needs to be a GET request. You need to set cache headers. It needs to be like an OK status code, essentially. And you need to set a content length. And it also can't be a large request or anything with a set cookie header. So this is good for static assets that is going to be common across multiple users. Doesn't have any personalized information or anything like that. Another really cool thing you can do is set URL maps inside the load balancer. You can basically say, send requests to my backends and send static requests to my Google Cloud Storage bucket. And obviously, all of that gets monitored and logged, and it's fronted by Cloud CDN. So what you need to do there, if you're backing URL paths with cloud storage, is to set the cache settings on your cloud storage bucket. Basically, you want to say, cache all of these assets. They're not going to change very often. Maybe you don't care if they get cached forever. You can be clever about changing URL paths or something like that if you need to flush the caches. There's also ways to flush the caches at the edge nodes. That's in the documentation as well. So this should reduce the latency, particularly for users that aren't anywhere near the zones of your backends. OK, so I'm starting to wrap up. We've looked at various aspects of application latency, or sort of perceived performance, comprising the performance of these network requests, whatever's happening on the device, including UI updates, whether you can do any tricks to send things asynchronously, both on the front end and the back end, and getting closer to your users to reduce that network latency. OK. But importantly, make it fast enough. Remember that story about creating blogs. Don't make it too fast, because your users might get freaked out. Take a completely holistic approach. You might have a front-end and back-end teams. Make sure they're working together to reduce the apparent latency for your users. Measure their actual latency from your users' devices, and test from real devices. You can use things like Charles proxy to introduce packet loss and latency and low bandwidth. There's also ways on the Android and iOS simulators to do this. Collect timings and metrics from your actual users and instrument your backends with tracing so you can figure out exactly what's going on. Consider your user's location, device, and networking capability. So again, simulating packet loss is a really good thing. Figure out how your app performs in poor conditions, and use global load balancing and CDNs. That's a really low-risk way of making things faster. But above all else, focus on user satisfaction. If your users are happy, then you probably don't have to do anything, right? Making things faster, you have to think about what impact that's going to have on your users. Maybe you can better spend that time that you would have spent on performance working on a feature or something like that. If you have the luxury to have multiple performance engineers or something like that, then this is great. Just keep investigating, figure out where things are coming from, and mitigate them. And that's it.